And Anil is an accomplished science writer and former staff writer at New Scientist magazine. He holds a background in electronics and computer engineering, having studied both at the Indian Institute of Technology and the University of Washington. He has an upcoming book to be released in 2024 with the title Why Machines Learn. He contributes regularly to various publications such as New Scientist, Quanta, Scientific American, and Nature. And currently, he's a journalist in residence here in Heidelberg. So please, Anil, the panel is yours.
Oh, thank you. Thank you, Helga, for that introduction. And welcome, everyone, to this panel discussion on generative AI. It's a pleasure to be here. So I would like to introduce our panel to you. But I have a confession to make before that. When the HLF organizers asked me to give them the order in which people are going to sit, because apparently that was needed for live streaming and putting their names alongside the faces, I very confidently sent them an email saying, this is the order of the participants in alphabetical order of their last names. And last night, looking at that list, I realized I had messed up. For one of the names, I had used the first name. But then I realized it's also a wonderful metaphor for today's generative AI, you know. So ChatGPT, for instance, will confidently tell you things even when it's wrong. So in keeping with my confident but wrong order, I'm going to stick to that order. And I would like to introduce our panelists to you, a very illustrious panel, I must say. To start with, Sanjeev Arora. Sanjeev, would you please join us on stage? He is the Charles C. Fitzmaurice. He's the Charles C. Fitzmaurice Professor of Computer Science at Princeton University. His research interests are in theoretical computer science and theoretical machine learning, and for several years now has been working on a new theory for machine learning, including deep learning. He's a member of the National Academy of Science and the American Academy of Arts and Sciences. He won the 2011 ACM Prize in Computing for his, quote, pivotal role in some of the deepest and most influential results in theoretical computer science and its applications. He did his PhD at UC Berkeley. Next, I would like to introduce to you Sebastian Bubeck. Sebastian is a partner research manager at Microsoft Research. Before joining Microsoft Research in 2011, he was the assistant professor at he was an assistant professor at Princeton University. He has won multiple awards for his machine learning results around robustness and optimization, including Best Paper Awards at NeurIPS. Most recently, he has become interested in understanding how intelligence emerges in large language models. With collaborators at Microsoft Research, he wrote the Sparks of AGI paper. A slip of tongue, I said he wore the Sparks of AGI because he's wearing a T-shirt. He wrote the Sparks of AGI paper, which we will hear about, I hope, during the panel discussion. The paper studies the emergent abilities of GPT-4. He did his PhD in applied mathematics at INRIA Nord Europe in Lille, France. And he has been a visiting scientist at Simons Institute at UC Berkeley. This thing about Berkeley will become clear in a moment. Next, I would like to introduce to you Margot Seltzer. And this is where I got my alphabet ordering wrong. Margot is the Canada 150 Research Chair in Computer Systems and the Cheriton Family Chair in Computer Science at the University of British Columbia. Her research interests are in systems, construed quite broadly, systems for capturing and accessing data provenance, file systems, databases, transaction processing systems, storage and analysis of graph-structured data, and systems for constructing optimal and interpretable machine learning models. She was a co-founder and CTO of Sleepycat Software, the makers of Berkeley DB. She is a member of the National Academy of Engineering and the American Academy of Arts and Sciences. She is the recipient of the 2021 ACM Software Systems Award, and the 2020 ACM Sigmod Systems Award, and the 2023 ACM Athena Award. She received her PhD in computer science from UC Berkeley. Finally, I would like to introduce to you Bjorn Ommer. Bjorn? Bjorn is a full professor at the University of Munich, where he's heading the Computer Vision and Learning Group. Before that, he was a full professor in the Department of Mathematics and Computer Science at Heidelberg University. His research interests include semantic scene understanding and retrieval, generative AI and visual synthesis, self-supervised metric and representation learning, and explainable AI. He is also applying this basic research to interdisciplinary projects within digital humanities and life sciences. His group has published a series of generative approaches, including VQGAN, and one that you would have heard of a lot, Stable Diffusion, again, which we will hear about during the discussion, which are now democratizing the creation of visual content and have already opened an abundance of new directions in research, industry, media, and beyond. He received his diploma in computer science from the University of Bonn and his PhD from ETH Zurich. Thereafter, he was a postdoc in the Vision Group at UC Berkeley. And when the panel came together, I was really intrigued by the Berkeley connection, because I started my career as a software engineer in Berkeley, working on large-scale distributed systems before I moved into journalism and writing. So I don't know what to say. Welcome to people from Berkeley.
It's the Berkeley panel.
So, sorry?
I'm from Stanford. Beat Cal.
Oh, I see. Okay.
Go Bears!
Okay, we're starting a turf war here. Before we start the panel discussion, I just wanted to go over a few basic things so that our panelists can focus on the more complicated conceptual issues. Most of you will remember this time last year. It was a much more innocent time. We hadn't yet heard of ChatGPT. But despite this loss of innocence, we are witnessing a remarkable moment in AI history, the emergence of generative AI, in particular image generation models like DALL and Stable Diffusion, and large language models like GPT-3, PaLM, GPT-4, and the like. In fact, even as we speak, these models are getting bigger and better. This is remarkable. Generative AI has been a difficult problem to solve effectively and efficiently. I mean, to understand why, it's worth going back about a decade. Machine learning models, whether they were deep learning models or otherwise, were mainly so-called discriminative models. And let's just take an example data set of images of cats and dogs, which the internet is full of, where each image has been labeled or annotated by humans as that of a dog or a cat. Let's say we want to train a model to distinguish between these two images, these two categories of images. The machine learning model learns the correlation between the patterns in these images and their corresponding labels. Then, when you show the trained model a new image that hasn't been labeled, it's able to categorize it as either that of a dog or of a cat. In essence, the model is implicitly or explicitly calculating the probability that the label is a dog, given the image, and the probability that the label is a cat, given the image. And depending on which of those two probabilities is greater, the model will assign the label cat or dog to the new image. It's essentially discriminating between these two categories. And you can, of course, extend the model to discriminate between multiple categories, not just two. And much of machine learning was focused on this kind of discriminative learning. But there's another kind of learning one can do, which is to learn the probability distribution over the data. So imagine some high-dimensional space in which the images of cats are here and the images of dogs are here, and each instance of data in this high-dimensional space is a set of pixel values that make up that image. Now, you can also imagine a probability distribution over that data, which peaks over the images of cats and peaks over the images of dogs, but it falls away elsewhere. What if you could learn or estimate this probability distribution? That's a much harder learning problem than discriminative learning, because the function you have to learn exists in an extremely high-dimensional space, but that's exactly what generative AI aims to do. Once you have learned this probability distribution over data, then you can use it, if you want, for discriminative tasks. Or you could do something more powerful and interesting, which is to sample from this distribution. Again, sampling from this distribution is not an easy problem to solve, But let's say in our example, when we sample from the distribution over images of cats and dogs, what we get back is a set of values for pixels of an image. These pixels will form an image that very likely is going to look like that of a cat or a dog. Now just imagine learning the probability distribution over all the images that exist on the internet or all the text on the internet and so forth. That's sort of what's happening now. And that's what we'll be discussing, that kind of technology during this hour. I briefly want to mention some terminology that will likely get used. The AIs that we're going to be talking about are deep learning models, which are deep neural networks trained using backpropagation. These are networks of artificial neurons. And so when the panelists refer to the number of parameters in the model, we are talking about the number of connections between these artificial neurons, which is a proxy for the complexity of the model. So with that introduction, let's start with the panel discussion. I'm just going to walk over to my desk and then, or my chair. So welcome everyone again. It's a real pleasure to be here. I want to start by a set of questions for each one of you to set the stage for further discussion. So Bjorn, can we start with you? Your team developed Stable Diffusion, the image generation model and AI, which made such a splash when it came out. Given the pace of the change in this field, it seems like a long time ago. But it was only around this time last year that the code was made public. Could you give us an insight into how Stable Diffusion works as an example of a powerful generative AI for images, and maybe differentiate it from the image synthesis AIs that came before?
Okay. Yeah, thanks for setting the stage beforehand already and distinguishing a little bit of what was going on in machine learning, deep learning beforehand, and generative AI these days. When we had been training discriminative approaches beforehand, that was typically based on a lot of data, so it was like supervised learning that we had. When we're training generative models, the beauty is actually in presenting like the infinite amount of unlabeled data that's out there, but not having to label that. Now, how do you teach a machine the structure that our world actually is made up of and presents to us without actually annotating that? And that is what we call like self-supervised learning. And there are different ways to actually go about. In the case of Stable Diffusion, for instance, you present the system with images, training data that you have, no annotations for these images. And what you then do is you add a tiny bit of noise to each of these images. A tiny bit of noise, you would not even notice the difference, but when you repeat this process of adding noise hundreds or even thousands of times, the end product will look like you plug the cable from your TV set. Pure noise, no signal there anymore. Now, why would you actually want to remove all the signal from an image? You do that to turn the process around and ask a neural net to actually take a noisy signal and remove a tiny bit of noise, because you have it, right? You have the noisy and a little bit less noisy signal. And that is a neural network that does this, autoencoder-like architecture, for instance. And the beauty now happens when you repeat this denoising process hundreds or thousands of times. You start with pure noise and turn that eventually not directly into the image that you started with, but something which is qualitatively similar to that. And there are different ways to go about in large language models, for instance. That's like blinding certain parts of your stimulus and then having the generative AI figure out what that actually is. What sets Stable Diffusion apart from the other approaches that were about there beforehand is that our goal was right from the bat to make sure that this technology works on consumer hardware. Consumer hardware for 300, 400 euros, usual graphics cards that you can buy. These days it even fits on your mobile phone. As opposed to, and that's what we were seeing back in the day, the trajectory going to only big companies having the assets to actually run generative AI, because it required during inference and even more so during training, big supercomputers for millions of dollars. And I saw this as for our society, critical technology, which will permeate through all different fields that we're having, not just computer science. And my goal was to make sure that the development, the future development of this technology stands on as broad a set of shoulders as possible, and not just in the hands of a few companies which have the assets available for that.
And in terms of understanding what the distribution on one side of this path that you described, there's noise on one side and the real distribution of images on the other side. Is this process allowing you to do the sampling process more easily? Because it would be hard to sample the more complex distribution.
So I guess this question goes in the direction, how do we then go about and make sure that this technology now works on much smaller hardware than beforehand? And that starts off with a very easy observation, and that is when you want to synthesize images, when we're talking about images, images consist of millions of pixels for you as a computer scientist. From a neurophysiological perspective, they're also super complicated in their representation. But at the end of the day, what you actually perceive there is not the hair on the fur of each individual hair on the fur of the dog, but what you just care about is there is fur. The average length, probably, the color of the fur, but not how each individual hair is actually pointed. So that sort of poked us and asked us, like, could we actually have a compression there, which is more alike to what we're having actually in our cortex going on, which figures out that it's not the individual hairs that you need to memorize. These you could then sample. You could learn what they actually look like, and with that get a much more compact model rather than one which gets obfuscated by all of these individual pixels that we actually want to render. So a two-stage approach essentially, and that helped then to democratize this AI.
Sebastian, I wanted to, there's a question for you now. You were one of the first to get early access to a beta version of GPT-4. This was even before ChatGPT was made public. And GPT-4 is now currently among the most capable of large language models. So before we talk about what you discovered with your empirical tests, could you give us a brief overview of how LLMs work in this context of generative AI for languages?
Sure, yeah, I can do that. So Bjorn already talked about the self-supervised learning, which is, I think, one of the two biggest breakthroughs that happened in the last few years. The other one is the introduction of the transformer architecture. So I think transformers were mentioned yesterday. It was introduced in a paper in 2017 titled "Attention is All You Need." So let me try very briefly to explain to you what is attention, and why is it different and why is it so striking. So before, those neural networks, for example, to recognize whether you have a cat or a dog in an image, they were convolutional neural network. What is a convolution? It just means you have some other image, like a small patch, and you're going to scan your big image with this small patch, trying to see if you find a pattern somewhere. Okay? So for example, maybe your little patch is going to be a circle, and you just scan the circle everywhere in the image to see if you can find a match of this circle. Okay? And those patches in convolutional neural networks that are being learned from data. Okay, so you learn a circle, you learn a square, you learn an ear, you learn all kinds of patches, and they are being applied repeatedly in the layers of the neural network. This was the classical stuff. I would call this an absolute machine in the sense that those filters are absolute. They are being fixed forever. They are learned, but then once they are learned, they are fixed forever. Now in language, with a sentence, like the meaning of a word, you cannot compare it to some fixed dictionary. The meaning comes from other words in the sentence. It comes from the context. So instead of having an absolute machine, what transformers do is that they become relative machine. So the filters, instead of being fixed, they are being given by the other words in the sequence. So now transformers, instead of being applied to a single high-dimensional vector like an image, they are being applied to a sequence of high-dimensional vectors. Each high-dimensional vector represents a word in the sentence, and instead of being compared to this bank of fixed filters, they are being compared to each other. This is the attention mechanism. The attention mechanism is basically for each word, you're going to look to which other word is it putting more attention towards. And you apply this repeatedly, and this is a transformer architecture. And this is really what has opened the way, I think, to the revolution that we're seeing now.
So in terms of actually training the LLM, once you have this architecture, what would be the process?
Right. So this is then the self-supervised learning process that we just talked about. So specifically for the GPT models, all you do is that you feed it a lot of text in the form of documents. And for each of these documents, you try to ask it to predict the next word. So you give it a partial text, and then you ask it to predict the next word. And that's all you do, on billions of documents with networks with billions of parameters.
And in the end, the model has learned the probability distribution over words now, some sort of conditional probability.
In the end, magic happens, and yeah, in the end you get GPT-4 and ChatGPT and all of those things.
So we'll come to that about what they do. Okay. So Sanjeev, you have been evaluating the capabilities of LLMs and developing a theory for some of the so-called emergent behaviors that we see today, particularly as these models get bigger and bigger, or they get scaled up in the lingo. So we'll talk about your theory in a bit, but for this round, could you tell us what we mean by the term emergent behavior and how that is related to scaling or the size of the models, and what's the connection there?
Okay, so emergence is a term that you may have heard about in this discussion. And what it says, just in a line, is that you measure how good the model is in terms of its modeling, like how its fidelity to the underlying distribution. And so that's one axis. And then the other axis is so that's the x-axis. And then, the x-axis is the number of parameters, and the y-axis is the fidelity. And so you look at how that fidelity changes with the number of parameters, and it is some relationship. And the number of parameters it goes hand in hand with the amount of data you need for training. So when you look at that relationship, there's some inverse polynomial relationship, and that's, so the fidelity is going as inverse polynomial of the size of the model, and that's the scaling law in a nutshell. What people also refer to when they talk about emergence is that, fine, so this relationship was observed empirically by very lengthy and expensive experiments in industry. But what people also discovered was that somehow, as the model starts getting close to the underlying distribution in terms of its predictive ability for the next word, suddenly it seems to get new capabilities. And in a nutshell, what happens is that there were hundreds or thousands of tasks in language processing, and one by one, the model just automatically solves them, essentially with basically no training examples. So I'm simplifying a bit, but that's the idea, that these capabilities emerge. So that's the term emergence. And there was it was introduced by people who probably had a physics background, and so they were very interested in rapid emergence. But I think, I believe, and probably many, that there's no rapid emergence. The model is just improving in some underlying way, and then suddenly at some point it's able to do some task. And there's no magic in the rapidity of emergence.
So it's not some phase change that's happening, it's a very gradual increase in capability.
Yeah, that's my view, and in my conceptual frameworks, and I believe that's, would you agree with that?
I think it's a complicated question.
Yeah, no, I know you've done some other.
Yeah, no, I mean, I think I mostly agree with it, but also it happens that at some point the error gets turned down enough that suddenly it's able to do the task much more reliably, much better than before. Correct. And this might happen in a slightly shorter window. Like there is a big difference between having, like 10% error and 1% error. If you repeat the task many times, then suddenly it's a big difference, because the task is being repeated. When you produce text with those GPT models, you produce one word at a time. So really, the difference between 10% and 1% error is being amplified.
Yeah. So indeed. So yeah. So because that measure is just predicting the next word.
Right. Right.
And so small changes there could manifest themselves in that kind of macro behavior. But so yeah, depends on what you're looking at. But I don't think there's any magic there.
Right.
That's hard to somehow mysterious.
There is no magic in the world. I don't want to give the impression there is magic in the world.
What eventually pops up then looks to us like magic, right?
When you first see it, and then you look at it carefully, and you say, yeah, no, that makes sense.
And where the grounding comes from, like in image models, for instance, like you did not train them to have reflections in water or shadows being cast, like what that actually even means for them. But if you just presented enough data, and if you have a powerful model that can learn these long-range interactions cross images, then that eventually emerges out there. And to that extent, it's something that you haven't explicitly sort of informed, but it's a regularity, if you so want, about the world that eventually sort of appears.
Right. Right. So, Margot, as you listen to this and as a computer scientist who has witnessed some key technological developments, we've talked about this. I wonder if the changes that are afoot with AI in general and generative AI in particular are making you wary. You know, you had mentioned you wanted to pose some questions for the audience to start with. So maybe you can do your polling and that will set us up for the discussion over the hour.
Yeah, that was a long time ago. You know, I guess so I've heard a lot of use of the term, you know, query engineering to get the right answers you want out of these large language models, which, to be fair, are incredibly useful. And so I am going to play the skeptic a little bit, a lot, we'll see. I appreciate your opening with the example. And actually, one of my students, not knowing I was on this panel this morning, posted to our group, and I want to share this with you because it seemed particularly relevant. Here we go. Okay, so this is a group I have that works in program synthesis, and we're trying to synthesize device drivers. And so he used GPT-4 with the Scholar AI plugin, and he said, and this is a way I actually encourage my students to use these tools, you know, could you find me similar papers to, and in quotation marks, he gives the title of a paper, Understanding Modern Device Drivers. Seems like a good query. If I asked you to do that, I am guessing that you would find papers on computer systems and operating systems and devices, and GPT-4 helpfully said, Understanding Modern Drivers in the Employee Experience in Healthcare. Slightly different than what we were trying to get to. And you could imagine a continued dialogue that would get to the right place. But what that really did was reinforce my really cynical view, which I'm always hesitant to state publicly because, let's be clear, hashtag not my area. Right? Let's just be very clear on that. But I am bolstered in my willingness to say this by something that Alexei Efros said earlier in the week. So I have been saying, you know, these are cool, they're useful, I have very specific ways in which I do use them, but they're babblers on steroids. I'm sorry. And then I was really gratified when I heard Alexei talk about them as, you know, Markov and Shannon had it right, and attention is really critical. And attention is really critical, and it has let these models do things. But I'm also comforted by the statement, like, it's not magic. And I actually fear that our biggest problem has been how we've presented these to the public. In that maybe everybody in the room knows that we have to be a little skeptical of the answers we get back from GPT-4. But I don't think we've done a good job of explaining to the public that they too need to be very careful about how they use it. We've already seen disasters. We've seen sorting disasters. I believe I was talking to somebody last night at the banquet with one. You know, but if we don't do a better job of actually explicitly helping people understand what these tools, and I think tool is a really important word here. We heard it the opening day from Jens Brandenburg. This is an amazing tool. It's a great tool. But we have developed many tools before, and we need to be careful how we use them, and we need to be really careful about how we encourage the general population to use them, because they're really great tools. They're incredibly misleading, but I am reminded of the phrase we used to describe one of my children when they were small, which was, sometimes wrong, never uncertain. And I feel like that describes GPT models pretty well, and we might all know that, but I don't think the people using them every day do.
Fair point. And I think that actually brings us nicely to the sort of next round of the discussion, which is this technical point about, you know, about 2 years ago, there was a phrase that was coined to describe how LLMs work, this phrase, stochastic parrots. This idea that LLMs are essentially regurgitating, albeit in a very sophisticated manner and, you know, albeit stochastically, but they are regurgitating patterns that already exist in the training data. This was a phrase that was probably very applicable at the time for those LLMs. You know, it would be nice to explore, you know, by talking to all of you, whether things have moved on, whether we see this differently now. So Sebastian, maybe this is a place where you can tell us about the kind of tests that you were doing with GPT-4 before it was released to the public, you and your colleagues put out a paper, the Sparks of AGI paper, about empirical observations. The paper created some ripples. So
Yes.
could you tell us about that and your conclusions and the reaction to the paper?
Yeah, of course. So first, I agree with everything that Margot said. I just want to be clear that I agree with all of it. But still, let's try to ground a little bit this discussion into what those models actually can do. And I think I will give you 2 examples, and then we can discuss whether there is any magic or not, or whether these are stochastic perils. So the first one is, I don't know if you had this experience, but somehow anybody, the first time they interact with ChatGPT, the first thing they ask is to write a poem. I don't know why exactly. I mean, it's kind of, if you think about it, it's sort of beautiful that, we all want to have this poetic interaction with the model. So that's what we did also. The first thing we did is we asked it to write a poem. And, being mathematicians, we asked it to write a poem about a proof. And, what better proof to us than, the most famous proof of all time, that the fact that there are infinitely many primes. Okay, so you all remember this proof, right? You just multiply, all the numbers, all the primes that you have so far, you add one, and then you look at the prime factors, okay? So let me pull out my phone and read just the beginning of the poem that GPT-4 gave to us. So this was exactly, I think, exactly a year and 2 weeks ago, we were in my office with Ronan Eldan, my good friend and collaborators. We put in the word just, write a poem. We asked, can you write a poem about the fact that there are infinitely many primes? And this is what we saw on the screen. Yes, I think I can, though it might take a clever plan. I will start by noting Euclid's proofs, which shows that primes aren't just aloof. Assume we have a finite list of primes and that none have been missed. Multiply them all together and add one, just to be clever. And he keeps going. I don't know. Personally, I get goosebumps every time I read this one. It's insane. It's insane. Who would be capable in this room to come up with this? I mean, in an afternoon maybe, but in like 10 seconds. Was this pulled from the internet? Who writes poem about the fact that there are infinitely many primes? Okay. And not only that, but we asked as a follow-up, we really wanted to push the model and really try to see, its capabilities. And we asked follow-up questions about the poem, which I will tell you after because I want to tell you another story. But it really kind of understood, it was showing real signs of understanding. So that's one example, okay? Let me tell you the other example, which is what's on my shirt. So I have a young daughter at home, and she likes to tell me about unicorns all day long. And I was using GPT-4 to tell her stories about unicorn. Okay, so I would prompt GPT-4, write a story about a unicorn playing with this doll, that doll, whatever. And it was working very well. And then one night I woke up and I wondered, actually, what does GPT-4 think that a unicorn look like? And so I asked it, can you draw a unicorn? So it's a very weird thing to ask because GPT-4, these GPT models, they are text to text. Okay? So how is it going to draw? So I asked it to draw, and it replied with lines of code. Okay? Once I compiled this code, this is the image. I don't know if you see it on the screen. This is the image that I got. Okay? I mean, I fell from my chair. This is insane. Again, completely insane. Of course, I mean, you look at it, it looks shitty. But that's the whole point. The fact that it looks shitty is much better. It didn't copy it from the internet. That's really what GPT-4 thinks that a unicorn looks like. It understood, okay, it has 4 legs, it has a body, it has a horn, etc. It's really striking. And by the way, for the mathematicians in the audience, this image was written in TXZ. Okay, so I have wasted many, many hours trying to draw things into TXZ, and just drawing 2 circles takes me an afternoon. Okay, so drawing this, I'm not capable of doing it. Now, again, still, one of the questions was about the reaction of the public also to the paper and to those examples. Some people said, okay, but there are examples of animals being drawn in TXZ on the internet. I mean, yes, of course, the model has to learn from somewhere. It didn't, how would it know how to draw a unicorn in TXZ if it had never seen an animal in TXZ, online? But it has been able to connect all of these different sources. the text describing what a unicorn looks like, the drawing of other animals into TXZ, and it has been able to synthesize it. And this act of synthesizing information, I mean, yes, you can talk about it as stochastic parrotry, but isn't this the essence of intelligence? I mean, it is the essence of what we do as mathematicians, trying to find the commonality between many different situations. So I think it's going far beyond, stochastic parrotry, in my opinion.
That's a strong position and well said. So, Sanjeev, you have been working on theory of emergence of behaviors, which is also, to you, suggesting that more is going on with LLMs than simply stochastic parroting. So, could you talk about, why your theory itself, and maybe why you think so?
Yeah. So, lay my cards on the table. I'm probably somewhere between Sebastian and the stochastic. Yes. Although I'm on one side. So I do think that LLMs have some eerie properties, and I've been trying to understand them. So let me first point out. I'll start by So stochastic parrots. I'll get to that by the end. But realize where it comes from, because when you train the LLM, you're trying to make it predict the next word. Now, prediction can mean anything. Turns out you use something called the logistic loss, and so if you actually look at it mathematically, basically, it boils down to matching the distribution in KL divergence. Okay, but that's a kind of arbitrary choice that you're predicting the next word using a logistic loss. You could use any loss. Okay, so that's it. So there's no magic about modeling the distribution. So one thing I've been trying to convince colleagues is that language models are not about modeling language in the statistical sense.
Sorry, can you say that again? Yeah.
Language models are not about modeling language.
Okay.
Okay. So, and that's not what the goal is. Like these people are trying to now create AI agents, and you're not trying to be a stochastic parrot, right? Good. So the people who are designing it don't think of it that way, and once I confront them, and they say, yeah, you're right. Okay. So then what? But still, by doing that process, which is technically modeling the language in a statistical sense, you get interesting behaviors. So with a colleague at DeepMind, Anirudh Goyal, we started thinking about it a lot, and the idea is that you posit that there is some underlying skills that we're interested in, right, in AI, and the text, instead of being a distribution, is like pieces of text with an arbitrary measure on it, arbitrary distribution, which is actually the way technically they are trained now. You have these different data sets, you give them arbitrary weighting. So, and then in that framework, and we assume that pieces of text combine random subsets of skills, and then for the discrete math people here, that's kind of has a very strong expansion or mixing properties. And using that, we can show that if you just minimize this prediction loss, you will be able to get competence and skills. Skills being elementary tasks that are being involved in these predicting the next word. So what happens is that skills emerge. But then the interesting thing for intelligence is composition of skills. And people here have thought about it, including beyond that, compositional generality. Like intelligence corresponds to being able to combine things you already know in an arbitrary way. And I think that at the heart of it is non-stochastic. I mean, it feels non-stochastic to us when we do this. And so why does that emerge? It turns out that because of that random graph structure, you can show that capability on k-tuples of basic skills also emerges. And the key point here is that the number of k-tuples of skills, for any reasonable number of skills, quickly becomes way bigger than the size of the training set. I mean, the training set is in the trillions, but still, k-tuples really blows that away. And so what we actually show is that, yes, mathematically, you do get competence in k-tuples of skills, despite never having seen any example of it. Just mathematically, there aren't enough examples. So that was a prediction of the theory, and we did an experiment, which is a paper probably just today or tomorrow sometime will appear on arXiv, where we tested that. So you give language models. We started with a list of skills, in linguistics and rhetoric and so on. There are lots of skills. So you take that long list of skills and take random k-tuples, and ask it to produce text. And then the grading task is actually fairly difficult. Even generation is difficult. It takes me 7 minutes. But then you use GPT-4 to grade it and do human spot checking. And yeah, we find that, for instance, the most powerful models like GPT-4 can do 5 tuples pretty well, which shows that actually they're not stochastic parrots. They are actually responding to tuples of skills which clearly, mathematically, had never been tried. So, for example, write 2 lines about in the context of sushi that involve hyperbole, ad hominem attacks, and a couple of other things, right? And you do, the number of such combinations is large enough that no human has ever written 2 lines about sushi with those combinations. But it'll give you a reasonable answer. So it's at least some demonstration of non-stochastic parrot behavior. It's not parroting back things it's seen. It has some level of compositional generalization. Now, once you realize that, you say, okay, why are we doing generative modeling in the first place? Referring to the title. So probably what we're trying to get at is this compositional ability, and probably there are other ways to get it.
Bjorn, I want to come to you in a bit about how this argument applies to image synthesis. But before that, Margot, you indicated that you're on the other side of the spectrum here. So those are pretty strong positions. So how would you like to
So I
respond?
want to respond by a question. So I think the question is, what do we mean exactly by statistical parroting? And we know that low probability events happen. They just happen with low probability. And so I guess when I hear statistical parroting, what I think is that this is a probabilistic model, and we're going to generate different things with different probabilities, and the prompt is going to skew those to different areas. But there's nothing in the example you gave that isn't obvious to me could arrive just by probabilities. And so when you say statistical parroting, what do you? I think you're taking a narrower definition than I am.
No. So I think the issue is indeed people haven't specified what statistical parroting is. So so Sebastian here got a lot of grief over his paper. I believe you'll agree.
It will be correct eventually, so I don't mind. But,
But I'm just saying that you got a lot of grief, and people say GPT-4 was trained with 15 trillion words or whatever, and nobody has seen that training corpus. Hence, we cannot know whether there wasn't a TIXI program that actually had a very similar thing, right?
I hope no human being draws like this, though.
No, actually, people found very similar things, right? So because we don't know the training set,
Right.
that can never be settled. And so, at least in our test, it's settled mathematically. Number of k-tuples is so large.
Right. Okay, so I completely, hold on. So I completely agree with that.
So you've never seen a k-tuple.
So I've never seen that particular k-tuple. But
Of
even
skills.
Pardon?
Of skills, even. Yes.
Totally agree. But that doesn't mean that I haven't seen, the 4-tuple, what am I trying to say here, right? That the probability of seeing the 4-tuple followed by the particular 5th element of the tuple has been given probability 0.
but then what would be outside of stochastic parrot? Maybe
what else is outside?
What is, if it can do everything, then sure.
If it actually learns the distribution.
Okay, let me think about that one, because I'm having a hard time articulating
So
what's
let me
going
say,
on internally.
Bjorn has probably thought about this a lot too, so we should weigh in. The moment you have compositionality, so there's language which is like statistical, right? And then because of composition, there's like just too many, right? So the moment you start getting that, you are going to see behaviors that were not in the training set. If that's in terms of skills, right?
Define skill.
Let's not even go into that. Like, it's a complicated thing, right? There's no fixed definition. Your intuitive definition. We'll agree that basic skills, there's like thousands, if not millions, right? If you include all our activities.
Okay, so let me try to use a stupid example and see if you can translate it. So a babbler produces sentences that we've never seen before, right? A simple, n-gram babbler, right?
Yes.
So it will produce sentences we've never seen before.
But they don't make sense. Composition means they have to make sense.
But some of them do.
Yes.
Right? But not all of them.
Yes.
So So again, I'm not trying to say that LLMs are babblers, but I can write a babbler that will, in fact, create sentences that make sense.
That's
even
all
though it will also
monkey
create,
typing. Yeah, that's the typing monkeys. Yeah,
a little bit like typing
Yes.
monkeys.
Yeah.
So now start there and get to your.
So instead of typing monkeys, you look at them and they're actually typing out sensible text, right? Like his unicorn. Then what do you say? Is it a stochastic parrot?
But I guess the question is, are all the outputs meaningful?
Right. So what you're saying is that this technology is very imperfect, and I'm suggesting, I mean, everybody agrees,
Yeah.
right? So that's why I said I'm between you and him.
Yep.
Or maybe even more extreme people than him who think it's. But the point is that the moment you have competent out of training set generalization, you have to start asking questions, right? Where is this coming
Fair
from?
enough.
Okay.
I mean, also the bar at being correct all the time, I hope it's not applied to any of us in this room.
Absolutely, absolutely.
Because,
and
you
yeah,
know,
getting into the fact that
so-
people aren't always right.
That's right.
But
Yeah.
go ahead.
But this is. I mean, you know, we were at a workshop on LLMs where Sanjeev was presenting this particular idea, and just this discussion itself, you know, between Alexei and you took about 15 minutes, and I don't think they reached a resolution during the conversation, but afterwards.
Yeah, I think
So-
he thought I was talking about like 1,000 skills, and he says there's no 1,000 skills. I said, take 1 billion, I don't care. The argument is even stronger.
So yeah, I mean, I guess the point I was trying to make is this is not going to get settled
Probably not.
that easily. But it is, I mean, it looks like there definitely is a kind of spectrum of opinions. And
No, I hope you change. I mean, you seem to like see
No,
that
I
there's.
appreciate. I think I may have stated my cynicism more strongly than is real, but I think that's useful.
I guess the
I
issue
wanted to
with
say
much
one
of
important-
that
sorry.
is that when we're talking about parrots here, I mean, there's always this looking of us as human beings on this machine and saying like, hey, it doesn't fully have the skills that we actually would expect of a true intelligence. But the question is, what do we actually really understand underneath that? And to what extent are we human beings are actually also then acting as parrots if we actually would portray it like that? And what I would find important is if we take a step back and think about what we're actually training there, because there's only this discussion about we working on artificial intelligence or machine learning or whatever else that is. But years ago already, there was discussion whether we should aim for weak or for a strong intelligence. Yeah? And I guess the consensus these days, like what most people are actually working on, is what's called weak AI. Sounds like bad or demeanor in that case, but it's as strong as the systems that come out. What's the difference there? A weak AI is supposed to give us something that acts rationally, sort of solves the task that we actually presented, as opposed to a strong AI, which is supposed to mimic human understanding of the problems that we're having. Like the classic example would be that of the Chinese room, where there's somebody in there who speaks no Chinese, but by means of the right rules, input in, right answers out. You have your ChatGPT system, so to speak, yeah, giving you the right responses there with zero understanding about what this system is actually doing. Still a helpful system. Is that a stochastic parrot or not? Don't know. I mean, that we have to discuss. There's a lot of situations where human beings act similarly and still produce sort of great results. I think so that's one thing that we need to be clear on, like what is actually our goal? And I think our goal should not be to replicate human beings or human intelligence to the full. At least that's what we're not really aiming for at the present stage, but produce something that then, what should it do? Generalize beyond the training data that we're actually presenting it. Now, we are looking at situations where we have humongous training data available, but still, compared to the complexity of the world that we actually would want to model, I would actually say that the training data is more like little islands in the Pacific Ocean with lots of water actually surrounding it. And what I believe, and with that I guess I'm standing also somewhere in between you there, what we're seeing is this intelligence, artificial intelligence, machine learning algorithms, starting to build bridges between these islands. Yeah, so in an IID scenario, we can see that the algorithm is actually able to kind of interpolate in between. besides generative AI, my team is also working quite a bit on deep metric and representation learning. So everything where you try to learn semantic relationships to get this out of the pixels that you have, because you know, like measuring the similarity between images in the pixel level is probably not the best thing to go about. So learn to portray that or to map that into a space where you can actually then mitigate semantic relationships. And this field is then all about transfer learning, going beyond the IID scenario. So where you've, and I believe this is like the true intelligence that we see among human beings, where you've been trained in one scenario, and then the world is changing, and you wait a few years, go to a different part of this planet, things tick a little bit differently, and then compositionality kicks in. How can you, with a finite number of rules, regularities that you've learned about the world, transfer that to different tasks? And with that, going back to what can actually visual synthesis approaches, for instance, do. For me, the kicker was really the work that we had before Stable Diffusion, the VQGAN paper, where we trained this AI, and suddenly it was able to actually learn things like reflections of mountains in a lake or shadows being cast without us actually forcing that into the system. That's not super great, but the generalization we see there is the system being trained on a bunch of objects that, when there is something bright in the top left corner, there's an object, then somehow there seems to be something darker to a certain angle. And the relationships, the spatial relationships, albeit this being all 2D, being somewhat okay. This then generalized to different objects that you haven't seen before, and is something that in human intelligence we typically sort of associate with compositionality. We don't have the time to go into that, which took a bigger part of my scientific career there, but something that we utilize to actually limit the complexity and make reasoning only possible. The only thing that I can say is, although I think we have dipped into this weak AI scenario, and with that I find it, we need to be a bit careful, like then talking things down, just being a parrot, because then here or there we do it with human intelligence as well. We see at the same time simplification strategies as we see with human intelligence happening as well. And the last tiny bit of the story, I had zillions of interviews after we released Stable Diffusion, and reporters came about and said like, hey, I typed in these 5 words and out came not the image that I had in mind of, going in the direction of what you said beforehand. And guess what? An image is actually worth
more than 5 words.
Yeah, more than 5 words. And with that, you end up with an entire distribution of, an almost infinite distribution of possibilities that we have there. Tells me that we are typically not aware of how fuzzy our human language and our understanding about the world is, and that probably explains also a lot of disagreements that we have with another.
Yeah, maybe I can just add one word about this is, you know, exactly that those AIs are beginning to build those bridges between these islands of knowledge in the data. That's the sparks of AGI that I talk about. That's the sparks of intelligence, you know? I mean, just, I don't see a better way to put it. It's not yet real intelligence. It's, you know, making tons of mistakes, but it is clearly beginning to build a more complete map, connecting all of this information together.
And this is great. I'm still looking for extrapolation, right? I mean, this is more like interpolation. The extrapolation is getting even more tricky, but we even don't know what's beyond the fringe, right? But we don't have any rules for a world that exists beyond that, and figuring that out is also tricky.
So, yeah, that was the discussion I was having with Alyosha Efros. He says, that's just, what you're talking about is interpolation. I said, I don't know what that is. You know, like, what is the difference between he couldn't, I don't know. Interpolation, extrapolation.
We're coming from the same field, so to speak.
Oh, well, right. You are in the same field as Alyosha, yes. So
this, I guess, the big question then is, where is this going? And we have this empirical scaling laws that have been established, which also are going to change if, you know, the nature of the data set changes and other parameters of the models change. But at least, you know, bigger generative AI models are going to get better. How far can this go? What is the end game? And, you know, are there bottlenecks? Do you foresee bottlenecks? Probably Bjorn, your work has addressed some of the compute bottlenecks.
So as I said before, and when we released Stable Diffusion, I was concerned that only a few companies would have the resources available. In the meantime, speaking even with those companies, I've seen that they are now also running in trouble. Why that? Because they're having much larger problems, much more data that they need to process, and with that, they evidently also don't have infinite compute available. We see this with GPT-4, that here or there performance has not fully increased, here or there even sort of been reduced in performance, with some trade-offs being there. I guess if OpenAI would have infinite compute available, they may in that meantime also have ended up somewhere differently. The point just being, we've over years got used to like Moore's law and things going on the way that it did with this exponential growth. This for CPUs has stopped quite a while ago. And with GPU computing these days, we can actually see between supply and demand. And with that, I don't mean just the number of graphics cards, but the compute that you get out of the individual one. Difference between of a factor roughly 9 times more demand, or models getting larger than what we have there on the supply side actually being provided. And very recently, 2 days ago, Mistral released again a smaller model. We see the research community, I believe, also embracing sort of this direction that Stable Diffusion pointed, that we should try also to get more out of smaller models, and that true intelligence is actually learning with finite resources and not infinite resources.
Maybe that's, so we have run out of time, unfortunately. So we won't have time to take audience questions, but there is a panel discussion about social issues and AI coming up. So, hold your questions for that discussion. But there was lots of other things that we could have talked about, but we really. Margot, I would like to give you the last word, because I think there are lots of questions that you are our alter ego in this case.
I just want us to do a better job of communicating with the public about what we're doing. And I think that's all our responsibility.
I think that assumes that we understand. Like, as a community, you have agreements.
Yeah,
fair enough. But what I learned from Martin's talk yesterday more than anything else is that these kind of disagreements and the range of opinions are absolutely crucial for getting us somewhere better. So I think this was a great example of that.
Maybe just something that the audience should know is that nobody on the planet knows where this is going. I mean, I think this is important, you cannot trust anybody. We don't know whether it's going to lead to AGI, whether it's going to stop at GPT-4. One thing we do know is that there is a ton of room for improvement. Like, there are many orders of magnitude of gains that we can get. We can make those models 1,000 times smaller and do exactly the same thing. We can do it with much less data. We can produce much less data. Like, GPT-4 is the first cut. It's the first try that humanity did at building a model like this, and this is what came out, okay? And we didn't try to, improve any of the aspects. So we don't know where this is going. I think that's important.
And in contrast to previous AI winters, what we have already achieved is not just a hoax, right? I mean, this is there, this is working, you can try it out, and here or there, it creates some value.
Yes.
Well, there were lots of other sort of technical issues that we could have talked about, hallucinations, also social issues to do with copyright, intellectual property, the generation of harmful content, etc. But this particular discussion was focused on the technical stuff. So thank you very much. So please thank our panel for the